Okay, Bismillahirrahmanirrahim. So where were we? So here I exported the optimized design scenario. So here you can check the specific alternatives we have defined. So these are the optimized design alternative which we have created using a Darwin designer. So after exporting that specific scenario having a specific physical alternative. Musa Khan said taso tatakapan ke pal mic. Elizabeth, please also mute your mic. Okay, after exporting this specific scenario and the alternative design to this specific scenario, I will run that scenario. So here you can check the pressure at each nodes. So I will just annotate by color coding these specific die of pipe. I want to so here you can observe that the okay, I want to get the legend as well. So the pipe having dia equal to less than the pipe and in between these two ranges showing a red color, while having a less than 3 inch of dia showing these type of pipes, and while the greater than 3 and less than 4 showing in a blue color. So you can also check that these pipes from here 5 inch of dia and 3 inch of dia of pipes. So based on Darwin designer, you can use the Darwin designer for the optimizing your water supply network. So I want to show you other thing in Darwin designer as well. That if you want to find the, for example, I want to create another event, or I will just do this in this event as well. Okay, I want to design for example, if I know about the specific nodes where there's some near to the industrial area or factories. So here mostly probably the chances of the probability, the high probability of uh, fire occurring in these localities. So if you know about these specific nodes, so you can design additional demand to that as well, or you can also design additional demand to the specific nodes based on your choice or based on your network. So here I'm just giving a fire demand to that node of 1000 GPM. So based on that, I want to calculate the optimizer run. Rehabilitation okay. I was just run. Should give me chemistry solution. I don't know why it's giving a one solution. So by increasing the demand at nodes, the cost also increase because of the die of pipe required to fulfill these specific demands. So you can check this solution that here is some violation at junction 14 because of the high demand at J15. You can also check the flows. There is a lot of violations because of we have sets a very less constraint that should be about 6 to 7 feet per second in a pipe, in a pressurized pipe. So you can export then specific scenario to the fire flow analysis. And then running that specific scenario, you can check the results. So basically, all of the most of the pipes have a dia higher than 5 inch. Showing the die. The Darwin designer have calculated the die of that pipe about 8 inches, or that by about 10 inches. Similarly for that. So basically, the die of pipe increases due to the demand at that big at this junction increases. So increasing the demand and junction, so the die of pipe increases also. I want to just annotate it by so here you can observe that the red pipe shows having a dia of 10 inches. The green pipe shows the die of 7 inches, while this light blue color showing the die of 8 inches. And similarly for these pipes, because of the demand at this junction is very high, so the die of pipe head so in this specific region also increases. So now I want to show you other thing in Darwin designer as well. Okay, for example, if you want to calculate the cost of this specific scenario, then you can select this specific scenario from here and just run the that manual. Okay, run that scenario. We show you undefined point postal. This will give me solution. So it's based on that specific base scenario. It gives me the cost of that specific scenario, the pipe or the length of a pipe involved in that scenario. If you want to calculate for the fire flow and power flow analysis, you can do that as well. While another run is basically for the manual design run. And manual design run is just basically you can design the manual pipe if you have a high experience and know about that pipe of that that pipe, die of pipe will be suitable for that specific group. So you can design manually that specific group, that specific die of pipe, and then you can run the Darwin designer. So that's it for the Darwin designer. I want to show you the Darwin clay batter. So basically Darwin clay batter we use, for example, if you design a water supply network and after 10 years or after for 12 years, there are some failures most of the in water supply network occurs, and you want to check the leakage and the different junctions and Sophia. Please mute your mic. For example, if water supply network after 10 years, the C factors of the pipes also decreases due to uh, the after long term usage. So the pipe at the start of the design, it should have a value of, for example, in the case of Hazen William, uh, C factor, it should have for a tactile iron, will have a value of 130. After 10 years, after 12 or 15 years, the value will decrease up to the 100 or 105, based depending upon the situation. In some situation, there is also the leakages at the different junctions occurs. So after 10 years or 12 years, if you want to find the leakage in the different junctions, or also want to find the rusting of that of pipes in this in the water supply network, basically the C value mostly decreases due to the rusting of a pipe. So you can find easily through Darwin collaborator, and you can also catch those individuals which you have connected to your water supply network non-legally. So you can then check also using the Darwin collaborator. So basically, to show you that how the Darwin collaborator works, it requires some real time or a good data in order to field data in order to initiate the Darwin collaborator. So I downloaded that from a Bentley, that water supply network. Basically, they have already defined the field data. So in order to calculate the Darwin to find the leakages and C factor for the different type of pipes, first you have to go to the field and to calculate the pressure at each junctions for specific time. So here I want to show you that where it is. Graphs. These some graphs they have created basically. So these are the okay. Okay. Basically, when you design a water supply network at the start of your design, or when you operate your water supply network, so at the start, the demands, the water supplying for a reservoir have a less demand, and this basically depends upon your the extended period simulations at the 6 to 12 6 a.m. to 12 p.m. The demand is high, and similarly, following the specific patterns you have assigned to each node. So based on that specific demand or not, the water is drawing from the reservoir throughout the day. So these are basically the design values the graph shows, while these are the values which are observed in the field. For example, after the 5 years, after the 10 years, you can observe that the demand is higher than the demand at the start or at the commissioning of your water supply network. So how to check that where that the why that the demand is increasing uh, at the specific for that specific network. So in order to check, we will use the Darwin calibrator. So in order to enter that specific values, I want to show you that how to enter the observed data. So for example, if you get that field data, then and you want to add this field data and that specific graph and to check the behavior and to compare the behavior with your the demands at the commissioning period with respect to the field data, then you can check easily by just entering these specific demands at the specific time intervals that you have uh, uh, calculated for the specific time of period for the specific node at the specific nodes. So basically they are just considering this pipe, and they have calculated inflow for that pipe for a different type intervals, and that enter into these tables. You can then enter the y values, means the inflows or at different time of interval of time at the throughout the day, and then observe that how it behaves when you calculate the data, field data after 10 years or 12 years graphically. So the y dimension showing the flow parameters. That's the flow parameter, numeric parameter. Okay, so this is how you have show the relevancy between these two types of data using a graph. Before starting Darwin designer, I want to show you something. So basically, when you design for a extended period simulation, for example, in options, you mostly up till now I show you that mostly for the steady state analysis here. So in practically, we mostly design for extended period simulation in order to run the model for 24 hours or the 48 hours or the 72 hours for 3 or 4 days, depending upon your conditions. You can also design, for example, from which time you want to run the model and for at which time date you want to run this model. So you can design these values here. So for running a extended period simulation, you can control here the different time periods of your simulation. And to run the extended period simulation, you have to design the different demand patterns. I will show you that what does it mean in a separate lecture, inshallah. So these are basically the multiplier which at each time interval, these specific multiplier multiply with the for example, where the pattern has been assigned. So for this junction, basically that part 1 pattern is defined or assigned to it. So based on the part 1 pattern, when the time reaches to the 0.254 hours or reaches to 1 hours, so that multiplier will be multiplied to the demand assigned to that. So based on that, at each time interval, the specific multiplier will be multiplied to that specific demand at specific junctions, and when calculate the demand, and based on the extended period simulations, the water will be drawn from the reservoir. You can also define that multiplier for a reservoir. So I want to show you that as well. So here, basically what they have shown, Here the value of 1 meter has been assigned to the reservoir. So the 1 meter means that the water is available at the height of 1 meter. It is basically showing the level of water. So basically, the pattern also is has been designed to this that reservoir. So so by 8 time step, the specific multiplier multiply with the that one, so it will calculate the level of water at the different time step. The patterns, by using that pattern, the water level has been calculated using that specific multiplier, and then using in a extended field simulation in order to show that how the water is supplying for the reservoir based on the water level available in the reservoir at the specific time interval. Okay, so I want to show you the Darwin calibrator. So after getting the data from the field, you will go to the Darwin calibrator. So basically, after getting the data from the field, you will then create a snapshots, for example, at hour 0.25, whatever you want to assign the name to it. So that depends on you. So that should be defined in a way that it should be understandable for everyone working with you. So for example, at 0 hour, that type of specific the grade data has been obtained for this that specific nodes and the discharge for the specific pipe. So these are the data obtained for the different type the specific junctions and pipes at different time intervals. After entering this type of data, so here I'm just want to find the leakage. I will show also. I will also show you the roughness group. Basically, roughness group we use it for the find the C factor or the Darcy-Weisbach roughness coefficient in order to determine the rusting of a pipe as well. So here I just want to find the leakage in a pipe. So here the specific, these are the specific junctions has been selected as a group to use these junctions and find where the leakage is occurring and showing that high much demand. So to do that, you have to select the specific junctions, or you can also select all the junctions involved in your network. You can also define, for example, if you know about the status of the pipe in your network, most of probably in after 10 years or after 15 years, there will be some pipes that failures there it has some failures will be occurs in these pipes and not workable. So you can also define these different pipes as well status, and you can uh, design that whether the specific pipe is open or closed. You can define here at the status limit. Similarly, so these are the different method used for the in a Darwin calculator in order to calculate the specific uh, leakages or the roughness coefficients for you. So so decreasing the value of head per footness point or flow per footness point, they are basically numbers. So by decreasing these values, it will give the best fitness value. Basing of the flow type, the different value linear, the square root, and log. Using that, it uses some functions in order to calculate, for example, the head at the junctions at 10-year previous, for example, at 2020, and then had calculated the at the 2030 where you have calculated the data and make the calculate the difference in between them and make a square of that. So by minimizing the different squares, it will give you the best solution. In that scenarios, it will minimizing the difference, but by using the absolute values of the values calculated at 2020 and the values you have observed and at